Greetings. My name is Aarya Arun and I am one of the authors of HiPAES, a novel high-performance parallel AES. My co-authors and I are from the Parallel Systems Research Laboratory at the Department of Computer Science and Engineering at PES University. We are located in Bangalore, India. In our short paper, we present our novel implementation of the advanced encryption standard that incorporates two-tier parallelism and obtains a significant speedup. We will begin this presentation with a brief refresher on AES, followed by the related work and our motivation to take on our problem statement. We will then look at our methodology, experimental setup, and results. The Advanced Encryption Standard, or AES, is a highly secure symmetric block cipher that works on block sizes of 128 bits each. It takes a single key, which could be of size 128, 192, or 256 bits, and performs multiple rounds of encryption on each block to get the final ciphertext. For a 128-bit key, there are 10 rounds of encryption on each block. We can follow the journey of a block with a 128-bit key as follows with the help of this diagram. The plain text is sent to the AES encryption function. The initial add round key is applied to the block, followed by 10 rounds of AES, of which the first 9 rounds or standard rounds include the following functions: byte substitution, shift rows, mixed columns, and add round key. The 10th round or final round does not include mixed columns. At the end of 10 rounds, we have the block's ciphertext. The decryption process has a similar set of functions, but it uses some inverse functions and uses them in a different order as well. As such, AES offers multiple sources of parallelism, both in the functions within a round and opportunities for pipelining across rounds. The number of rounds depends on the key size, but for simplicity, I will use the 128-bit key example, which we call AES 128, throughout this presentation, and this has 10 rounds. AES is widely used today to encrypt a lot of sensitive material, hence an efficient implementation is required. Without optimization, the cost and runtime of AES would turn to be unmanageable, which may lead to users preferring less secure options. AES computations could also require a significant number of resources, which could be limited in embedded systems. Our objective was to capitalize on both sources or tiers of parallelism known to achieve a significant speedup. We did this in the electronic codebook or ECB mode, which is the basic mode of AES as explained in the previous slide. We have also worked with the counter or CTR mode, which will be explained in a later slide. Earlier literature has focused on in-round parallelism or parallelism solely within the functions of an AES round using loop unrolling with OpenMP and similar tools. Some have focused on hardware pipelining using FPGAs, but still others have worked on data parallelism where each block of plain text is encrypted separately in parallel across many processors. Even hardware pipelining and software parallelism implementations have required the usage of many processors in earlier literature. Our implementation combines in-round and across-round software pipeline parallelism, making it a two-tiered approach that consumes lesser resources than data parallelism, as it does not require multiple processors but a single GPU. As AES operates on blocks of size 128 bits or 16 bytes, we here focus on byte-level operations. Our first tier of parallelism is in-round parallelism, coming from the add round key and mixed columns functions. Add round key directly performs an XOR between the input to the round and the expanded round key. Each XOR is performed parallelly in our implementation as shown in the diagram to the left. The mixed column function operates on the 16 bytes of a block as though it were a 4 bytes into 4 bytes matrix with 4 columns, each column having 4 bytes. Each column can be operated on separately without affecting the output of the mixed columns function. And so we exploited this source of parallelism as well, with each column being operated on parallelly. This concludes our first tier of parallelism. We achieved this tier of parallelism using a concept called dynamic parallelism. CUDA allows for the host function or main function to launch a kernel. In our case, the kernel is the AES encryption function. CUDA allows child kernel launches or the launch of kernels from within a kernel, which it terms as dynamic parallelism. Here, the mixed columns and add round key functions are child launches, hence we employ dynamic parallelism in this particular tier. Our second tier of parallelism and pipelining comes from across the round pipelining. With respect to AES 128, we have 11 pipeline stages, which include the initial add round key and the 10 AES rounds. At any given point, up to 11 blocks of text are being encrypted under the pipeline. Our AES function calls a round function that receives the blocks that currently require encryption at any point in time. The blocks are sent to the round function through a carrier array as shown in algorithm 1 to the left. The carrier array can hold up to 11 blocks in the case of AES 128. The position of each block within the carrier array indicates how many stages of encryption it has already gone through. A new block is loaded into the carrier array at the first position or index 0. Once it goes through one stage of encryption, it is shifted one position to the right in the array and allows a new block into the array at index 0. The index of the block denotes how many stages of encryption a block has passed through. The round function uses this index to encrypt each block accordingly as shown in algorithm 2. Once a block has gone through 11 stages, it is removed from the carrier array and copied back to the plaintext array while all other blocks shift to the right by one position in the array. A new block enters the array at index 0, denoting that it has not been through even one stage of encryption. This process is carried out till all the plaintext blocks are encrypted and constitutes our second tier of parallelism. With the AES counter mode, there is a completely different system of encryption. An initialization vector, a nonce, and a counter block are used to compute a pre-key stream that is the same length as the plaintext. This pre-key stream is then encrypted with AES using the given key, which results in a key stream. The key stream is directly XORed bit by bit in stream cipher fashion with the plaintext to give the ciphertext. We applied our scheme in the context of CTR as follows. We let the pre-key stream computation take place serially, and we applied our scheme to the encryption of the pre-key stream only. Post that, the bitwise XOR of the key stream and the plaintext was also done serially. We took this approach because we wanted to stay as true to the serial CTR mode as possible, even when our scheme was applied, as our parallelization applies to the AES encryption itself and not necessarily the entire mode. Our scheme was still applicable to the key stream encryption. For our experimental setup, we used an Intel i7-9700 CPU, which is octa-core, with an NVIDIA GeForce 1650 GPU with 16 GB of DDR4 RAM. We used the CUDA toolkit for our parallelized code and a single SM. We used plaintext of 3 different sizes in our experiment: 9,000 kilobytes, 12,000 kilobytes, and 15,000 kilobytes. We also made sure to encrypt each plaintext multiple times and also with keys of all possible sizes. We encrypted each plaintext document with each key size multiple times and took the mean of our observation for final results. We compared all our schemes against a serial ECB implementation of AES in C++. We then also ran our experiments using the same plaintext documents and keys in the CTR parallelized scheme, comparing it against a serial CTR implementation as well. In this slide, we present all the ECB schemes that we ran experiments with. In addition to our proposed methodology, we incorporated 2 other factors in our ECB experiments. First was the use of AES and I instruction set, which we see in our first scheme, where we compared the serial ECB implementation with a variant of itself that has the AES and I instruction set enabled. Second, we experimented with our proposed scheme and the usage of CUDA pinned memory. As per CUDA, pageable memory belongs to the host. When data is transferred from the host to the device, we can use pinned memory to keep a section of the memory reserved for variables whose values are often sent to and received from the device functions. Pinned memory makes data transfer between the host and the devices faster. The next 4 ECB schemes are as follows. First, dynamic in-round only parallelism or tier 1 parallelism without the usage of pinned memory. Next is the dynamic in-round only parallelism with pinned memory. Next, we have the 2-tiered pipeline scheme without pin memory, and lastly we have the 2-tiered pipeline scheme with the usage of pin memory. Apart from this, we have our CTR mode AES implementation as well. Now let us look at our results. In this first graph, we present the data of all observations made using a key size of 128 bits in the ECB mode. The x-axis denotes the plaintext sizes and the y-axis denotes the speedup of each scheme over the serial ECB implementation. Each bar denotes one of the 5 schemes we experiment with in the ECB mode. We see we do not get much of a speed up with the AES and I implementation. However, all the other schemes give a speed up of close to 3 times. The best speed up we have achieved is using the dynamic in-round only parallelized variant without pin memory usage, as well as the 2-tiered pipeline variant with pinned memory usage. In our next graph, we show all our observations made using the 192-bit key in the ECB mode. The x-axis again denotes the plain text size, and the y-axis denotes the speed up of each scheme over the serial ECB implementation. Each bar denotes one of the 5 schemes we experiment with in ECB mode. Here again, we do not get much of a speed up using AES and I. However, the other schemes provide a speed up of 3 times or greater compared to the serial ECB version. We get our best results with the dynamic in-round only parallelized version without pin memory, as well as the 2-tiered pipeline version with pin memory, which are the same schemes that stood out in the previous slide. In our third slide, we present the data of all observations made using a key size of 256 bits in the electronic codebook mode. The x-axis again denotes the plain text size, the y-axis denotes the speed up over the serial ECB version, and as usual here, the bars denote the schemes that we use in our ECB experiments. We do not get much of a speed up again with the AES and I implementation, but all other schemes give a speed up of 3.5 times or higher, up to 3.6 times, especially with our dynamic in-round only parallelized version without pin memory and our 2-tiered pipeline parallelized version with the usage of pinned memory. The reason we see that the pinned memory variants do not give too much of a speed up in comparison to their non-pinned memory variants is that the encryption and decryption functions in our implementation are totally device functions. This limits the number of times the data has to be passed between the CPU and the GPU or the host and the device. Had there been more occasions to transfer data between the host and the device, pinned memory would have made a much larger difference. This final graph shows our CTR mode speed up compared to a serial CTR version. Here the x-axis denotes the text sizes, the y-axis denotes the speed up of a scheme over the serial CTR version, and the bars actually here denote the different key sizes with which we encrypted our text sizes. Here we see that we're not able to get a speed up of greater than 1.4 times with all our schemes in all the text sizes as well. This entire graph only speaks about the CTR mode scheme and no other scheme. We see that the speed up is not huge. This is because the only place where the scheme or the parallelized pipeline implementation was applied in the CTR mode was in the pre-keystream encryption. The rest of the components of CTR remain serialized, so the overall speed up from start to finish is not much. In conclusion, in this paper, we proposed a novel, sophisticated, high-performance, multi-stage parallel AES, obtaining a speed up as high as 3.6 times by simultaneously exploiting both in-round and across-round pipeline parallelism using a single streaming multiprocessor. The implementation is scalable and works well with all key sizes and also consumes fewer resources. This concludes our presentation. Thank you.